Good morning, DiffyQs. This is Friday, and this is a lesson on um, homogeneous differential equations with constant coefficients. And one of the classes yesterday did derive Euler's principle. It was the class I call the purple class. The other class, the all boys class, we have not derived Euler's principle yet. And that is something that I wanted to do in person with you. So there are going to be parts of this for the all boys class that I'm going to say, and you'll see how this relates when I see you on Monday, I believe. So in other words, there's like you guys are off by one class, and so I want to just make sure that you're aware of the fact that I'm aware of that. Okay. All right. So when we have constant coefficients, and if you want to look at one, the last one we did together, a homogeneous differential equation, this was one we solved. Okay. And we used the characteristic solution of e to the mx. And we kind of posited that the reason why y equals e to the mx is a characteristic solution is because the nature of e to the mx's derivatives is such that you get the original function returned to you either intact or with just a constant multiple. So you can conceive of how a constant times iterative derivatives of e to the mx could cancel out. What we also talked about, though, if you remember, is there are other functions that have that unique property, namely our circular functions, sine x and cosine x, right? So e to the x, sine x, and cosine x have the unique property that the starting function and at some point its iterative or higher derivatives can cancel. And when I say cancel, I mean add up to zero, okay, in some kind of constant multiple fashion. This is from my all boys class. Oh, actually, no, both of you. We defined linear combination, right? A summation of constant multiples of, all right? So, we talked about the fact that e to the x, or the family of e to the mx, sine of some constant times x and the cosine of some constant times x has that unique property that its linear combination of iterative derivatives equals zero. For the all boys class, we have a name for an entity whose sets linear combinations equals zero. We called it linearly independent, right? Or linear independence. So once again, I would write this down somewhere. The exponential function and the cosine and the sine functions have the unique property that its linear combinations of iterative derivatives are independent. That is very unique, okay? Now, for my all boys class, when I say here that y equals mx is always the characteristic solution, and you say, well, what about sine x and cos x, Miss Yam? You just said that they also have that property. What we haven't done yet, but my other section has done, is we've showed that y equals e to the mx actually includes sine and cosine by way of Euler's principle. So my all boys class, when I see you the next time, that's the first thing we will show, is that y equals e to the mx includes sine x and cos x, okay? Which is yet another one of the really interesting features of Euler's principle. Characteristic number 2, for HDEs, the order of the Diffie-Q, which means the derivative level, so to speak, right? The order of the Diffie-Q will always equal the number of unique solutions, okay? And the reason behind this is very simple. It's because of the polynomial property of, do you remember when you studied polynomial equations back in the day, and you had to solve something like this? Okay? And you recall that back in the day, this degree 5 equation, if you include complex and multiplicities of solutions, the total number of solutions should absolutely equal 5. Now, remember, you kind of built up to this point. We started by finding, all the real solutions, and then we started finding the imaginary solutions, and then we started counting multiplicities of solutions as also unique solutions, okay? So the polynomial property that the degree of the equation equals the number of unique solutions if you count real, imaginary, and repeated, Okay, that is the reason why HDEs also must have a number of unique solutions that equals its degree. And the reason, the reason why it is applicable here is, remember in this example that we did maybe 2 classes ago or 2 Zooms ago or 2 asynchronous lessons ago, I've lost a little bit of track. When we solved this and we went ahead and put in, the characteristic solution, or when we subbed it in rather, you'll remember we did this. Okay, and when we subbed it into the DiffyQ, go ahead and pull out your notes if you will. You remember that we got this at some point. Right? And then this ended up being a factorable quadratic in this case. So the reason why this principle holds is because, as you can see, the order of the DiffyQ for a homogeneous differential equation with constant coefficients, now that's our focus, okay? The order is immediately related to the degree of this quadratic equation that ends up being the source, the root of our solution path. This expression inside becomes so important to us because that's what we in effect set equal to 0 to solve for m and then solve for our unique solutions. And so important is this, so that expression inside and this accompanying equation, that some textbooks refer to this as the auxiliary equation, okay? The auxiliary equation that results along the route of our solution of the HDE in the first place. Okay, so that is why property number 2 holds. Okay, so as far as HDEs with constant coefficients, we've talked about property 1. Incomplete for my all boys section because you don't see how it is that EVMX relates or includes sinusoidal functions. We'll get to that. Property number 2 we just discussed. Okay, property number 3 we've partially discussed. So there are 3 cases when we start looking at, and you'll see here because I'm focusing on degree 2, okay? Actually, I'll just do this. We're going to talk about, in this case, second order for the most part, only because higher ordering factoring techniques like factoring by grouping or factoring by way of synthetic division, my suspicion is you probably forgot. And if we go to like order 3 DiffyQs or order 4, if we go to order 4, those will be factorable by quadratic form. If we go to, order 3 or higher, I'm going to try and search for ones that are factorable by way of a GCF, okay? But, I'm only focusing on second order because factoring a quadratic is just the simplest at this point, okay? But just to be clear, higher order are not more difficult. They just beg the question, do you remember how to factor by grouping? Or do you remember how to factor by looking for patterns like difference of cubes and sum of cubes, okay? All right, so there are 3 cases. If b squared minus 4ac is greater than 0, and by the way, make sure we understand, when I say b squared minus 4ac, I'm referring to the auxiliary equation, right? This quadratic that results, okay? If b squared minus 4ac is bigger than 0, we know that we have 2 distinct solutions. And I partially worked this out, but you can go through and look at your notes and see and confirm that when we solved this, let's see, I believe we got y equals c1e to the negative 2x plus c2e to the negative x as our general solution, right? Okay, because we found the 2 values for m, we used the principle of superposition, and this is our final solution. Let me just double check that. I just did this quickly, right, by inspection. Minus 2, Yep, good, okay? So let's take a look at case B, all right? So case A we've addressed. What about for case B? All right, well, let's take a look. What happens if we have a second order HDE like this? And once again, we have a second order HDE, constant coefficients. Therefore, this is my characteristic solution. And yes, I'm going to say it for probably the 4th time. The all boy section, we will definitely talk about how this ties into sinusoidal. And then I just did a simple substitution here, okay? And I factored the e to the mx out. and I'm here, and I get m equals -3. Okay, so m equals -3 is a root of the auxiliary equation here of multiplicity 2. So I know that one of my solutions is C1 equals e to the -3x, okay? But I know there has to be a second solution. Now, this is where I want to distinguish something. So in the world of polynomial equations back in the day, if you were just asked to solve m squared plus 6m plus 9 equals 0, and at the end of the day, you said m equals -3. Well, back in the day, you have found both solutions to this quadratic equation because m equals -3 counts twice, so to speak, right? It's a root of multiplicity 2, okay? However, this auxiliary equation is not the original differential equation, okay? So the differential equation has a second unique solution. So what I'm distinguishing here is I'm teasing apart the fact that, yes, m equals -3 here for the auxiliary equation, and if we were just solving for the auxiliary equation, we'd be done at this point. But unfortunately, this multiplicity 2 solution of the auxiliary equation does not count as the second solution for the diffie-q, okay? But the good news is we do know one of them. I'm not going to say bad, I want to say opportune news is that there is a second solution. How do we know how to find a second solution if we're given one solution? Well, remember the proof right here of this? This was the message I sent to you when I was saying I'm a little bit dismayed that some of you didn't watch the proof. And then the very next day, I saw a flurry of activity viewing this. We know that we can find a second solution by way of reduction of order, okay? And was that called reduction of order? I actually forget. Is it reduction of order? We reduce the order. Anyway. Oh, yes, it was. The derivation involved reduction of order. Anyway, so what's the second solution? Well, let's take a look. So here's what I did. You have to be very careful with all my subscripts here. So here is y2. So the second solution, which is what I'm looking for, is equal to y1, or the first solution. So y1 is right here. Here is y1, times the indefinite integral of e raised to the indefinite integral of -px dx. Okay, remember, we have to remember what p is. P, back over here, p is, here's the general form. I call this Q, right? Okay. P is this constant function of x. Now make sure that when you look for P, yes, the coefficient of y double absolutely has to be 1. So no big deal in the world of constant coefficients. You just divide by that constant coefficient if there is one. That's not 1. And then you have an updated P, but that's P. Okay? All divided by y1 squared. So here's where I just inputted everything into here. Be careful because y1 squared, right? So y1 squared, it's c1 squared e to the -3x squared, properties of exponents, e to the -6x. Look at that. Beautiful. Now I'm going to do this. What did I do? Yes. So from the next step to this step to here, I integrated e to the -6, which gives you -6x, hence e to the -6x is here, right? Notice that this inner integral has been addressed. I actually pulled the c1 quantity squared out of the integral because we can do that with constants, and that's why you see it here, all right? And then I hope your eye is caught by this, right? The antiderivative of 1 dx just equals x. So there's my 1. Okay, and then what I did was I just called, this function c1 over c1 quantity squared. You can certainly call it 1 over c1 if you want to. I just called it c2. It's going to be just some new constant. And here is my final answer. So my second unique solution is c2 times x times e to the mx. And you will notice that... Oh, whoops, what is that? It should be -3, excuse me. It should be -3. And you will notice that this is of the form C2x times y1. And there is my second unique solution. So I'm going to go back over here and say, okay, my second solution is y2 equals c2x e to the negative 3x. What that then allows me to do is state the fundamental general solution. The general solution is a linear combination of y1 and y2. So the general solution, I'm going to call it y, is c1 e to the negative 3x plus c2x e to the negative 3x. I have something that I'm sure will land very nicely for you all. A natural question you have is, when you have case 2 being, where's case 2? Here we go. When you have case 2 being b squared minus 4ac equals 0, your question is, will the second solution, will this y2 always have the form of c2x times y1? The answer is yes. So in this case, could you skip all of this? The answer is yes. Okay? And that concludes our lesson for today. The reason why I don't want to go into case 3 right here is because if I go into case 3, I absolutely lean heavily on Euler's principle. And for one class, I haven't derived it yet. So I'm going to hold off on that. Okay? I will post homework with this screencast on the teacher page. Have a great Friday and a wonderful weekend, everyone. Great job.